Hello everyone. So this is going to be just a very quick, short, 5-10 minute video on organic synthesis. It's just a very small topic in A2 organic chemistry. Not much to it. You're probably going to be at best getting a 1 or 2 or 3 mark question. That's about it. Not a big question. So what you're going to cover in organic synthesis is all about what do you think of when you're trying to do an organic reaction. You've studied all your organic reactions. You know how to convert a benzene into, let's say, chlorobenzene. You know how to react or do nitration of phenol. So, you've studied all these reactions. So, we're just going to give you a very small, brief background on what to think of, or what do scientists or chemists think of when they're trying to, let's say, make a dye in the industry. What is the reasoning behind the conditions that are chosen, and what is the thinking behind that? So let's just quickly cover this. So the very first thing that a chemist would actually look for is what are the reagents needed for the conversion. So that's the first basic thing. Like if I want to make chlorobenzene, from benzene, what reagents do I need? I need benzene, and I need chlorine, and I need an AlCl3 catalyst to go with it. So that's the first information that is required or needed, which you've already studied. You know what the organic spider charts are. You know how the reactions are going to be carried out. The second thing is you need to be aware of the presence of other functional groups, which may be there, but you don't want them to react. For example, if I want to make methyl benzene into, let's say, chloromethyl benzene. Now there's a methyl group, it's an arene, so there's a methyl group that's over there. So you have to be worried about that you don't want that to be disturbed. So you need to be aware of the other functional groups, and the reagents that you select. You need to be aware of what will happen to these other things that are also present in the molecule. You might be trying to convert, let's say, CN into carboxylic acid. You're trying to hydrolyze it, but maybe there's an ester group in it as well, so that also gets hydrolyzed. So you have to be aware of the effect of your reagents on these other functional groups that you're not trying to convert into any other thing. The third one is obvious. You're going to go for the conditions. What kind of conditions are suitable? Pressure, temperature, catalyst wise. What would be suitable for this particular conversion? So those are the conditions. Number four is you're going to be worried about the rate. You want the reaction to happen quickly. Hopefully, it should not take a long time. Hopefully, it happens. It doesn't take a month for the reaction to happen. You're doing it industry. You're doing it for a profit. So you want the rate of the reaction to be good. You want the yield of the reaction to be good as well. A reaction that only gives you 1% yield is a terrible reaction, especially when it comes to industry. Like 99% of your reactants are not taking part in the reaction. So you don't want that to happen. So you're also aiming for a good yield as well. Then fifth one is obviously economics. All of the above. What is the cost of the reagents? What is the cost of maintaining a pressure, maintaining a temperature? About when you're going to buy a catalyst, is it going to be expensive or not? Is the rate sufficient enough? Is it going to give you a good yield? So that all kind of boils down to economics. You're trying to get good economics out of it. You're making a medicine, you want to make it cheaply, so that you can earn a profit. So economics is a top priority. You're also going to be worried about the safety and the toxicity of the chemicals that you're using, about the whole process, what damage is it causing to the environment, and are your products safe? For example, you might be making paint, and that paint could have really harmful effects and could have cancer causing reagents in it, and you'll be embroiled in lawsuits. You might go to jail for making a medicine that's toxic. So you got to be worried about that as well. The next one is you'll also suffer with problems associated with purification. You want pure compounds. So some chemicals are really hard to purify, especially when you're doing a chemical reaction. There would be a lot of other reagents mixed with it, and maybe the product is not 100%. The yield is 40%. So there's a lot of unwanted chemicals that are still part of the product, and you want to purify it. So you have to have good processes which you can purify the product very, very easily. And now the very last one is stereochemistry. That's something that we're going to focus, since a lot of questions would be actually revolving around this last one. So stereochemistry is that when you make a molecule, you might end up with two versions of the molecule, which could be stereoisomers of each other. So here's an example. You might end up with mirrored versions of each other, and especially when you're making molecules, especially related to biology. Biology is really, really sensitive to molecules, to stereochemistry. One of them would work, and the other one might cause this one might cause side effects. So that is going to be a huge problem, because when you're making molecules, it's going to be really hard to make the right one. So you're aiming for this, and maybe you end up with this one in the product. So that leads to further problems. And biology, remember, is really, really sensitive to stereochemistry. It's really sensitive to the three-dimensional geometry of the molecule. Shapes are extremely important in biology, because just as an example, like your two hands are mirrored versions of each other. If you see a glove of the right hand, then only your right hand can fit into that. If you try to fit your left hand into that glove, because of the different orientation of the bonds and the shape and the fingers pointing in different directions, your left hand will not fit into a glove that is made for the right hand. And that is exactly how biology works. It works in active sites. You've got enzymes. One molecule shape has to fit with the other molecule shape. Only then will the molecules be able to react or combine with each other. So that really, really matters in biology. So in biology, a lot of harm in medicine is caused by side effects from unwanted optical isomers. So because of stereo chemistry, one isomer would work, the other one would not, and it might have dangerous side effects. And the problem with laboratory reactions is, especially the synthetic synthesis is man-made. You would end up producing a lot of optical isomers. And now, this one solution for, especially in the medicine industry, is that you refer to natural molecules like herbal medicine. Nature has kind of become an expert at making always the right type of stereo molecule, having the correct orientation of the bonds. For example, we are made from an optically active amino acid, but nature has figured out when it does protein synthesis, it always picks the right type of amino acid with the right shape to go with the protein structure. So naturally, we can depend on natural molecules. We can go for herbal medicines, and that would produce fewer side effects because of the dangerous side effects produced by chemicals that are produced in the laboratory, because they have the wrong enantiomers. Remember, enantiomer is the term that is used for optically active isomers. So here I've listed some of the consequences if you're not going to make the right type of stereoisomer. Uh, that first thing is that separation in the laboratory can be expensive and complicated. Making the right type of stereoisomers gets really complicated, and if you don't separate it, you'll have a lot of side effects. And because of side effects, dangerous side effects, you could go into a lot of legal action as well, especially when it comes to medicine. And larger doses would be needed. For example, if you're making a simple molecule of let's say flu, uh, now you know that 50% of the optical isomer of the same molecule that you're making are not working properly, while only one version or one geometry or one stereo isomer of the molecule is working. Then you would need a larger dose, because if you're producing and remember, stereochemistry blows up. It's an exponential function. Like if you have two chiral carbon atoms, you'll have four different three-dimensional arrangements. If you have four different chiral carbon atoms in a molecule, that's 16 different three-dimensional arrangements of the molecule. So geometry of the molecule. So there would be 16 different stereoisomers. So if a molecule contains more and more chiral carbon atoms or more double bonds which are forming geometric isomers, the number of possible geometric shapes would be a lot. And that complicates things, and you would need very, very large doses for that. Now, solution is depend on natural molecules. They would have less issues with chirality. And the more complicated ways or methods are that there are certain reactions which are stereoselective, which means that they result in only one type of stereoisomer. The catalysts which help you making the right type of stereoisomers as well, and there are certain enzymes which can be stereoselective as well. So we're not going to go into details that complicated ways of making the right type of stereoisomer, but those ways are complicated. So now I'm just going to quickly cover a few examples of where stereochemistry becomes a challenge. So let's go for it. The first reaction I'm going to study is it's the nucleophilic addition of carbonyl compounds, aldehyde and ketones, which you've already studied in AS. So here you can see the reaction. I've got an aldehyde over here, ethanol. HCl reacts with it. You need an NaCN catalyst, and that results in the formation of a cyanohydrin. So you've already studied this reaction in AS. So what I'm going to discuss now is I'm going to show you how stereochemistry is going to affect this reaction. So let's focus on the shape of the molecule now. So when carbon has a double bond, that's trigonal planar or fan shaped. So what you see over here is the same aldehyde but drawn in a three-dimensional arrangement. This is the actual shape of the molecule. Think of it as a trigonal planar shape, fan shaped. Think of it as a fan, completely flat with a carbon that's positive, which is going to attract the CN-1 over here. Now think of it as a flat fan shaped molecule. So now two things would happen. Now one of the version is that the nucleophile CN-1 is going to come in, and it's going to come from the top and attack this carbon atom over here. And if that happens, so imagine it coming from the top. So here I've drawn the consequence, the CN coming from the top and all the other bonds are getting repelled in the downward direction. So it forms a tetrahedral shape, and that's a cyanohydrin. The carbon has a CN and an OH. If you know the mechanism properly, the oxygen becomes negatively charged and then it attracts the H+1. So I'm skipping a few steps, but the idea is, what I wanted to show you is that the CN is coming from the top, it's bonding to it, and all the other bonds, the fan shaped, think of these as blades of the fan, they're getting repelled in the downward direction. Or the other thing that can happen is that the fan shaped molecule, the CN-1 could attack from the bottom. And if that happens, now what would be the shape of the molecule over here? So if that happens, the CN is now bonding from the bottom now. So if you look at these two molecules now, they're basically mirrored versions of each other. How are they mirrored versions? Like if I pick one of the molecules, and I'll just show you, although this is not as obvious, but if I pick this molecule and I bring it over here, then you'll notice that both molecules are, and let's show this over here. So you'll notice that both molecules on your screen are basically mirrored versions of each other, and the probability of getting both molecules, it's an equal chance. Why? Because you got an equal probability of the CN attacking from the top, forming one of the stereoisomer, or the CN attacking from the bottom and forming the other stereoisomer. So just as an example, remember that nucleophilic addition of carbonyl compounds, the synthetic route is, you know what the synthetic route is. The idea that I'm going to give you is that in this case, both types of chiral products are possible. Both types of enantiomers are actually possible. And remember, enantiomer is just a fancy word for optical isomers. So from now on, whenever you use the word enantiomer, that just means an optical isomer. That just means the molecule has a chiral carbon atom and it's forming two non-superimposable mirror images. Now we're going to discuss the stereochemistry of another very common reaction that you've studied in AS again. That's the SN2 mechanism. So what happens in the SN2 mechanism is that you have a halogenoalkane, and the OH-1 nucleophile attacks it, and the carbon, what happens is the Cl gets knocked out and OH replaces it. So let's assume that this is the SN2 mechanism. So what happens in the SN2 mechanism? Now here's the three-dimensional representation of the same molecule. The carbon is positive and the Cl is negative. Now because the Cl is slight negative, what will happen is that the OH with its lone pairs and the OH minus 1 nucleophile is always going to attack from this side. It's going to attack from this side, and what it will do now is the Cl over here will get pushed out. It's going to get pushed out, and the OH would bond and come in and bond from this side. So let me draw what the product is going to be. So here is what the product would look like. So if you can see, what's happening is the OH is coming in from this side, and so the OH is coming from the left side and bonding with this carbon atom, and the Cl is getting knocked out. And all the other bonds, they're getting pushed to this other side. They're getting repelled by the OH. So the negative OH comes in, it repels all these bonds to the other side, and the Cl gets knocked out. So every time you're going to get one version of the optical isomer, that's about it. So every time you're not going to get both versions, just one version of the optical isomer, which is this one. You're not going to get the mirrored version because the OH is always going to attack from one side. So in the SN2 mechanism, the OH always decides to attack from one side because that's the other side is negatively charged. So the negative OH is not going to attack from that side. So it always comes from this side, all the bonds get pushed to this side, and you always get one type of optical isomer. So here I've written that down, always approaching from one side, always, and only one optical isomer is always produced. Now let's also talk about the other mechanism, which was known as the SN1 mechanism. So I again have the same tertiary halogenoalkane that is producing this chiral carbon alcohol. And we're going to talk about the SN1 mechanism, which is slightly different compared to the SN2 mechanism. So what happens in the SN mechanism is that in the first step, the Cl gets knocked out, and that results in the formation of a carbocation. So here you can see step number 1 for the reaction. You can see the Cl getting knocked out, and that results in the formation of a carbocation. Let's focus on this carbocation. And in the next step, the OH minus 1 comes in, bringing its lone pair of electrons, and it bonds with the carbocation. So I'm going to focus on this particular step, this one, and I'm going to look at the shape of the molecule. So let's focus on this carbocation, and let's try and draw the shape of the molecule as well. So what will happen in this case is that this carbon is bonded to 3 atoms. So that means this carbon is actually it's going to be fan shaped. It's going to be trigonal planar. So I've drawn this carbon over here. In reality, it's going to be fan shaped, all bonds repelling each other, so it's going to be trigonal planar. And the middle carbon over here, that's the one that's positively charged. So the OH minus 1 is coming in, and the OH minus 1 has two choices. It can either bring its electrons and bond with this carbon atom from the top, or vice versa. It could come in with its lone pairs. It's going to come in and it's going to bond with this carbon from the bottom, and that would result in two different types of stereoisomers. So here you can see I've drawn both the mirrored versions, the OH coming in from the top, all the bonds repelling downwards. So that's one mirrored version. The other one is the OH1 attacking the carbon from the bottom of the fan, this trigonal planar shape, and bonding with the carbon over here. All the other red bonds, they're getting repelled in the upward direction. So these two enantiomers or optical isomers are going to be produced, and they will be produced in equal quantity. Why? Because there's an equal probability of the OH minus 1 attacking from the top or from the bottom as well. So just a quick recap. Just remember just a little bit of stereochemistry and the factors that are affecting it. And also remember, you're not going to get a big question, a very big question on this. So they might ask you about an SN1 mechanism, and they might ask you, why are you getting two chiral carbon atom molecules? So you're going to describe that the carbocation that's formed in the middle, that's a trigonal. It's got a trigonal planar arrangement, and the OH minus 1 in the next step, the nucleophile can attack from the top, or it could attack from the bottom as well. So whenever you have a carbocation forming in any of the reactions that you've studied, both types of optical isomers are possible, mirrored versions, and they would have equal probability, and that's how you're going to describe it. The other one was you're going to describe about, let's say you got an SN2 mechanism. So in that case, what you're going to do is you're going to tell them that the OH minus 1 always attacks from the side opposite to the Cl atom. So which is why it always results in one chirality. The OH minus 1 cannot attack from this side because that side is already negative. So just very, very basic 2-3 mark questions.